Today, we bring you an upgrade of gpfdist, the multi-threaded compression transfer mode. In this mode, gpfdist utilizes the parallel computing power of multi-core CPUs to achieve efficient data transfer with less occupied bandwidth. The main content of this presentation includes the background of this upgrade, the implementation method, and the performance test results. gpfdist has always been a high-performance ETL tool suitable for GPDB. However, its high performance comes with substantial bandwidth usage, which impacts the network usage of other processes on the same machine. Moreover, its transmission performance is heavily dependent on network bandwidth, resulting in suboptimal transmission speeds in low-bandwidth environments. Therefore, this upgrade of gpfdist focuses on addressing these two pain points by adopting a multi-threaded design for data compression and transmission. The new version of gpfdist achieves a speed improvement of approximately 10% in the testing environment, while saving more than 60% of bandwidth. In new version, you can enable multi-threaded compression and transmission mode by using the new flag, multi-thread, and configure the maximum number of working threads. Alternatively, you can enable single-threaded compression mode with the flag, compress, to reduce bandwidth usage. The current gpfdist adopts the architecture shown in the diagram on the right to handle GPDB's data requests and send data. The key drawback for the current architecture is that gpfdist consumes too much network bandwidth, which affects other processes using the network. And its data transfer performance is limited by the network environment. So we came up with the idea of saving bandwidth by transmitting compressed data, but it also brought significant performance issues. Through testing, we found that the transmission speed was greatly reduced compared to the original mode due to the addition of compression tasks. Although it saved a lot of bandwidth, the performance loss was unacceptable. In the new version of gpfdist, we have introduced a new multi-threaded compression and transmission architecture. Upon receiving a request, we locate the thread that is serving the request. After the main thread is reclaimed, it checks for and handles errors that may occur during compression and transmission. The main thread then reads the file, generates new worker threads, binds them to the request, and performs data compression and transmission. In such an architecture, bandwidth usage is reduced by transmitting compressed data. By parallelizing the compression of data across multiple threads, we fully utilize the multi-core CPU performance of the server, improving the overall data throughput speed. There are two key points in the design. Requests are matched one-to-one with threads, which not only suppresses the uncontrolled growth of thread numbers, but also synchronized issues between threads caused by multiple threads processing the same request. Errors are only marked in the subthreads and are not processed. This avoids the need to protect shared resources between threads, reducing performance overhead. Through the above design, we avoided common thread synchronization scenarios in multi-threaded programs and reduced unnecessary waits caused by interdependent threads. This maximizes the efficiency of multi-threaded compression and transmission. To validate the effectiveness of the new architecture, we conducted comprehensive performance testing. We used 6 machines, 1 for the master node and 5 for the segment nodes, to build a test GPDB cluster. One machine is designated as the gpfdist running machine. The specific configuration is shown in the diagram on the right. The experimental data has a total size of 51 gigabytes, containing over 400 million rows of data, with 16 attributes per row. Through the experiment, we obtained the following data. 1. While transferring 51 gigabytes of data, the multi-threaded compression transfer mode took only 25 seconds, whereas with traditional transfer mode took about 29 seconds. 2. In terms of transmission speed, the multi-threaded compression transfer mode is about 15% faster than the normal transfer mode. Meanwhile, the bandwidth occupancy of the multi-threaded compression transfer mode is only about 40% of that of the traditional transfer mode. Through experiments, we have validated that the approach of compressing and transmitting data with multiple threads is not only faster than the original gpfdist, but also saves more than 60% of the bandwidth. However, in the experiment, We found that the bottleneck that limits the transmission speed of gpfdist lies in reading files and filling buffers. To achieve better results, we can consider splitting the transferred data and launching multiple gpfdist instances for processing. By distributing data using multiple processes running concurrently, it can help break through this bottleneck. Thank you for your attention to the development of GPDB. We will continue to work hard and provide even more useful features.